Okay, so then let's start. Today, it's an easy topic. So we are going to discuss Nijenhuis operators in dimension 2. And so this is somehow special case when all the kind of the general facts and general ideas so can be simplified in a way. Okay, so what we are going to discuss? So first of all, so that what we will do, we will rewrite this Nijenhuis condition, the condition for a given operator to be Nijenhuis operators. We will rewrite this condition in a very simple form. It's going to be just the one very simple vector relation, and we are going to use to explore this relation. So today to discuss examples and properties of Nijenhuis operators in dimension 2. So I will explain. I told you already that Nijenhuis operators can be reconstructed from the trace and determinant, more precisely from the coefficients of the characteristic polynomial. But in this case, in dimension 2, we have only two coefficients, trace and determinant, and that I will explain explicitly so how this reconstruction can be done. So then we will see that this reconstruction leads to sort of a problem of description of special type of singularities of smooth maps, so-called admissible singularities. We will talk about operators with real eigenvalues, with complex eigenvalues in dimension 2. With it, I will try to draw some kind of portraits of Nijenhuis operators, and then we'll talk about the Jordan block in dimension 2. Okay, so Nijenhuis condition. So let us consider just an arbitrary operator. So in dimension 2, operator defined on a smooth the manifold of dimension 2 and 2. So what we are going to do today, almost all constructions will be local, just local. So we will consider point, a neighborhood of this point, and so we'll write down operators in local coordinates. So I fix some local coordinates x and y, and then my operator becomes just a matrix, 2 by 2 matrix with 4 functions A, B, C, and D. If my operator is just arbitrary operator, not necessarily Nijenhuis, so then so these 4 functions A, B, C, and D are not just arbitrary smooth functions, so no restrictions. Of course, so if I want this operator to be Nijenhuis, so there should be some relation between A, B, C, and D. And what we are going to do first, so we are going to describe these relations for these 4 functions, so that guarantee that this operator is Nijenhuis. Yeah, so here is the theorem. So L, this operator with 4 entries A, B, and C, and D, is a Nijenhuis operator. So if and only if, so the following vector relation holds. What's written here in the right-hand side, in the left-hand side, sorry. So this is a differential of the determinant of L. I will think, sorry, X. I will think of a differential of a function as a row vector, so which consists of, in our case, of 2 components: partial derivative with respect to x and partial derivative with respect to y. So d differential of the determinant, so it's a row vector with 2 components. Differential of the trace, it's a similar thing. So this is a row vector with 2 components, and I multiply it with matrix of this form. So it's, if you look at this, it's not L. it's some matrix which is produced from L in a certain way. So what is that? So this is this is a matrix which is well known in linear algebra. So this matrix is called the adjugate matrix for L. Adjugate matrix. Then I don't know if I should remind you this definition, or so what is that adjugate matrix? When you compute the inverse matrix for L, so then you compute it, so you take a matrix which is exactly the adjugate matrix of L and divide it by the determinant of L. So this is a standard formula, and this is a definition of the adjugate matrix. So you can think of it as the inverse matrix of L multiplied with trace. So that's basically, that's the definition. Okay. And for the 2 by 2 matrices, so if L is A, B, C, and D, so then of course you know that the inverse matrix of L is 1 divided by the determinant AD minus BC, and here's the matrix DA minus B, so minus C, so like this. So this is that is the adjugate matrix. Okay. So in other words, I can rewrite this the matrix relation in slightly different way. So to like this, the determinant, the differential of the determinant of L is you take the adjugate matrix, but since this matrix acts on covectors, so that's for this reason I put star here, and apply it to the differential. So I remind you once again. So it's if we talk about so dual operators, that's operators with stars, it means that we apply two row vectors and multiply not on the left but on the right. So it's exactly so what is written here. So this is the same thing. Good. Is it so? This condition here, is it somehow unexpected, or we should expect something like this? Where does it come from? This relation one. No, in fact, so we have already seen something similar. So you remember in my lecture 2, so when we discussed the elementary properties, basic properties of Nijenhuis operators, so we proved so this result. The result which shows how the differentials of determinant and trace are related to each other. So that's what we prove this identity. But so if I now, so if I rewrite this identity in slightly different form, so like this, yeah. So then so that I will get exactly our relation. So using the fact that determinant L times L inverse, this is exactly the adjugate matrix. Okay, so we need to show this. So in one way, so we know that this is true. So if the L is a Nijenhuis operator, so this relation holds true due to so this identity which we have already proved previously. So we need to prove the inverse statement, so other way around. So let us do it. If you look at my next slide, so that is that you will see the proof written in I would say in tensor form. So So we use here the standard tensor notation, Lij, coordinates with denote them the x1 and x2, and you can read this proof at home. I still say I didn't try it yet, but I wanna try to prove this fact, no sort of so independently and using this notation. So let's see if I succeed. If I do it correctly, I will derive this fact. If I make a mistake, then you will help me probably. Okay, so I want to prove. So I want to prove this relation. So the differential of the determinant of L equals the differential of the trace of L multiplied with matrix D minus B minus CA. And I want to say that I want to check that so this relation here, so this relation is equivalent to the Nijenhuis condition. Okay, so that I will write down Nijenhuis condition, and then we will compare this condition with Nijenhuis. What is Nijenhuis condition? Nijenhuis condition, you know, so this is L square xi eta minus L xi eta minus L xi L eta and plus bracket of L xi and L eta, and this must be 0. So that's the condition so we know. So this is the definition of Nijenhuis operator. So okay, so what is xi and what is eta? So these are arbitrary vector fields. In dimension 2, so we have two basis vector fields. So xi so equals d by dx, and eta so dy. Should I consider anything else? No, because so I only need to check this condition for the basis vector fields, and since there are only two, then that's what I need to do. So I substitute these two vector fields, and if this the condition holds true, then so we are done. So that is the point. So I only need to compute an Nijenhuis torsion for two basis vector fields, and as a result, so we will get so how many conditions. So this is so one vector relation. So for the vector with two components, so I will have just two equations, and here, by the way. So we also we have two equations. So this condition, and we basically need to show that that one pair of equations is equivalent to the other pair of equations. So this is a good exercise, and so let's spend some time to do that. No, first of all, so the first term. L square of xi and eta. Xi and eta, they commute. So dx dy here, so this is 0. And for this reason, the first term simply disappears. Then, okay, so L minus, so what is L xi? I take my operator L, so L is A, B, C, D. And if I apply this operator to the first basis vector, so I will get AC. So that's the first column. So this is A dx plus C dy. I apply it to eta. Eta is dy. Good. And minus L xi is dx, the image of dy, so this is the second column, so bd, this is b dx plus d dy. Okay, and plus then the last term, Lxi is a dx plus c dy, and L eta, so it's b dx plus d dy. So this must be equal to 0. So that's the condition. Good. So now let us compute all these brackets. It's minus L. This bracket. You know how to compute two brackets. So if I apply these differential operators, the first one to dy, so I will get 0 because coefficient is constant here. So other way around, I apply dy to the first component and with minus. So if I apply it, I will get minus a y dx. I differentiate the components with respect to y, minus c dy. Okay, minus here L, which I do the same. So bx dx plus dx dy. And so then this term, there will be more terms involved here, so I applied a dx to the second term here. I will get a bx dx plus dx dy. Then I apply here next term, so this c, so plus c, differentiate with respect to y, by dx plus dy d by dy to dy, and other way around, so with minus b ax dx plus cx d by dy, and minus d a y dx plus c y. So finally, so I need to compute the result of the application of L to this guy. So I will rewrite this in this form. Let me write it like this. So L, and so I apply to a y minus bx.
cy, it should be cy. You missed y. Cy partial. No, the brace above the brace. It should be cy partial y. You missed just.
Yeah, you're right. Yeah.
Cy
partial y. Yeah, correct. So a y minus bx here dx plus cy minus dx dy. So that's the expression in brackets. And so if I apply L, I know that so L applied to dx. So this is a. I will write it down. So a y minus bx L to dx. So this is a dx plus c dy. And for the second term, plus cy minus dx L dy. So this is b dx plus d dy, something like this. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is many, 6 or 16 terms here. Okay. So that is my relation here. And now for next, I want to write down this relation here. So for the determinant and trace. So the determinant of L, this is AD minus BC. So AD minus BC, so partial derivative with respect to x, AD to minus BC, so partial derivative with respect to y, so should be equal to the differential of the trace. Trace is a plus d. So this is ax plus dx, derivative with respect to x, and derivative with respect to y, y plus dy, and we multiply with this matrix d minus b minus ca, just like this. So what do we get? So we will get again we will get two equations. So let's write them down. For the first component of the row vector in the right hand side and in the left hand side. So here I will have axd plus dxa minus bx c minus cxb. For the second component, a yd minus dya plus minus byc minus cyb. Okay, and that is equal ax plus dx to d and minus a y plus dy c. So this is the first component. So this must be equal to that. And then the second component is minus b ax plus dx plus a y plus dy. So like this. So basically, where are the components for the two equations so in here. So this expression is 0, right? So this let me draw this. So this is 0. So that is 0. No, but this is a vector, and so what I should do, I should equate terms with the dx and so with dy, because dx and dy, so these are basis vectors, and as a result, I will get again two equations. Now we need to check that these equations are actually the same. Let me try to maybe to try to see this not just from without writing anything else. Term a, let me see, abx. Where is abx? no, this term abx dx, abx dx with minus. So this term, so this term cancels out. This term, and this term, they cancel out. Next, I will consider terms, coefficients in front of dx. CBY. So CBY. So CBY, let me see that. So this term here, CBY, and I have here similar term, so CBY. Next, BAX. BAX, it comes here, BAX, and it's a similar term here, so BAX. Next, DAY. DAY, so here it is, so DAY sitting here, and DAY sitting here. So next,